As we saw earlier with our demonstration with the water, equilibrium is both a forward and a reverse reaction taking place at the same time. The problem is this is taking place at a microscopic level. When something is taking place at a microscopic level, we cannot see it with our eyeballs. Okay? Microscopic means that it is happening, we just don't see it. In the container, after I was still pouring water back and forth, one was at a higher level than the other. The fact of the matter was there was still water being poured from the large beaker into the small beaker and water from the small to the large. But after each pour, the level was still the same. It was still at the same volume. So even though we couldn't see anything changing, there was still a forward reaction happening, there was still a reverse reaction happening. This is the point of equilibrium. What is going to end up happening is as reactions take place, they start with a lot of reactant and not a lot of product. As the reaction begins to take place, as we saw with the chapter on kinetics, the rate initially will be extremely fast. If we were to draw a graph of it, where we were to take green to be our reactants. When we first start, our concentration of reactants is very high, and our concentration of products, being red, is 0. Oh, that was supposed to be red. Of red is 0. So initially, as this reaction begins to take place, the concentration of the reactants will decrease rapidly. At the same time, the concentration of the products will increase rapidly in the opposite direction. And as this takes place, what ends up happening is, like we saw before, when we were talking about first order rate laws, the reaction will actually level out. For the products, the same thing will take place. The reaction will level out. And we'll get to a point where both of these reactions, the red reaction for the products forming and the green reaction of the reactants going away, will both become flat lines where the slope of this line is 0. At that point, we understand that the products are forming, these products are forming at the same rate that these reactants are going away. So remember, just like in this picture of these beakers, just because the quantities are not the same does not mean that these are not at equilibrium. That's exactly what we're seeing here. Remember, this was a measure of concentration of our stuff. If this was concentration with reaction progress, as the reaction takes place, initially the reactants diminish quickly. The products are formed quickly until we get to a point where there are less reactants. The reactants are still being formed by the products going in the opposite direction. The products are being formed as the reactants are going. So we get both reactions taking place. And at this point, when both of these lines are running parallel with a slope of 0, when both of these are going like this, then we are at equilibrium. Not before that, and not until that point. So now as we continue, if we look at this new reaction of hydrogen gas reacting with iodine gas to form hydrogen iodide gas, we can look at this as being an equilibrium reaction. Multiple people over the United States, over the world, lots of chemists all over the place have done this experiment, and they have found that at the point where equilibrium is reached, the relationship between the amount of hydrogen iodide and the amount of hydrogen and iodine in the container is constant. It ends up being the same amount all the time. So the relationship that we have here is what we call an equilibrium expression. The equilibrium expression is going to be what we introduced briefly when we were talking about kinetics. That was when we talked about K equals the concentration of products divided by the concentration of reactants. But what we're going to look at is each individual thing, and they're going to have an exponent based upon the coefficients in the balanced equation. So to make this easy, to use the example that is written on the board here above, we have hydrogen gas with a coefficient of 1, we have iodine gas with a coefficient of 1, and we have hydrogen iodide gas with a coefficient of 2. If I were to write this equilibrium expression, what I would end up getting would be K equals the concentration of HI. Notice that there's no 2 written here, but it's to the second power, divided by the concentration of the hydrogen gas to the first power, also divided by iodine gas to the first power. This would be called the equilibrium expression for this reaction. And what we have is this value of K is called the equilibrium constant. This equilibrium constant is a constant for this reaction at a given temperature. Now, if we change the temperature of our reaction, we're going to change the value of K. This expression, products over reactants, is always going to be true for an equilibrium reaction. So, if we were to take any other balanced equation and try to do it with that, it would be exactly the same. Let's look at the reaction of nitrogen reacting with hydrogen to form ammonia. Again, this is a balanced equation with a coefficient of 1, a coefficient of 3, and a coefficient of 2. To write the equilibrium expression for this reaction, K is going to be equal to the concentration of ammonia squared divided by the concentration of nitrogen to the first power, I'm not going to write the 1, but you get the idea, times the concentration of hydrogen to the third power. All we're doing is we're taking products, those things on the right-hand side of the equation, they go on the top of our fraction. We take any reactants that are given, and they will always go on the bottom. It is always, always, always products over reactants, raised to the power of their coefficients. What you will see a lot of times in books and a lot of times in a general discussion of equilibrium is an equilibrium expression that looks like this. They're going to use a generic equation of AA, where the lowercase letters are the coefficients, the capital letters are the species. So I have this balanced equation where A, B, C, and D are lowercase letters are going to be numbers. A, B, C, and D capital letters are going to be whatever the chemical formula for that substance is. And when we write an equilibrium expression, it will be K equals the concentration of C to the little c times the concentration of D to the little d divided by the concentration of A to the little a divided by the concentration of B to the little b. So there are going to be a couple things that we need to keep in mind when we do this. So what do we need to keep in mind? What we are keeping in mind is that these square brackets, when we write them, are talking about concentration. Concentration means usually moles per liter. We're usually going to look at it in the sense of it being molarity. Now there are other things it could talk about. It could be just moles. It could be, well, it's usually moles or molarity. And so we're going to look at it in this standpoint. If I look at this and I were to say, how can I change concentration? All I need to do is change the volume. If I were to change the volume, I could change the concentration without adding any more moles of my stuff. So this concentration becomes important because when I'm doing equilibrium expressions, if I have a chemical equation that has things that are gases or things that are aqueous, I can use them in the equilibrium expression. I'm already not liking the way that this is sounding. I feel like I'm confusing myself and confusing you. So we're just going to show a couple examples of what we're talking about. If I were to take sodium solid plus chlorine gas and let those things react together, it's really not going to be very much of an equilibrium. But we are going to form sodium chloride, which is a solid. So what we need to think about is, what does sodium chloride look like in the sense of it when I have it in a pile? If I were to take sodium chloride and I were to make a pile of this solid, this is the solid NaCl, would I be able to express it in a concentration? Would I be able to say how many moles per liter there are? And the answer is usually going to be no. But even if I could, let's just pretend that this pile represents a size of, say, 500 cubic centimeters. Okay? If that were 500 cubic centimeters, and I wanted to change its concentration, that would mean I'd need to change its volume, or I would need to change the number of moles. Well, if I change the number of moles, what am I going to have to do? To get more moles of NaCl, I'll have to add more powder. The volume is going to get larger. So if the volume gets larger, as I add more solid, that means this volume is not 500 cubic centimeters anymore. Now the volume is going to be larger, and I have more moles. So actually what we end up seeing is when we increase the number of moles and the volume goes up at the same time, at the same rate, we end up with a constant. And so I cannot use solids when I'm doing equilibrium expressions. So anytime I'm writing a balanced chemical equation, so here, this wasn't balanced, by the way, I needed a 2 here and a 2 here. But in order to write this equilibrium expression, I have this thing that's a solid. I can't use that in my formula. And I have a solid here. I can't use that in my formula either. all I would be able to use would be the concentration of the chlorine. So if I'm looking at this from an equilibrium standpoint, this is an example where it doesn't look good at all. This equilibrium is only going to be based upon the concentration of the chlorine gas. I'm going to drop out the solids because solids concentrations don't change. Even if this were at equilibrium, if sodium were reacting with chlorine to form sodium chloride, and the sodium chloride were breaking apart, say it was at a high enough temperature where the sodium chloride was able to break apart back into chlorine and sodium, this concentration would not change. The amount of solid that I have there is going to determine the concentration. I can't change the concentration of a solid. I'm not sure how clear that was regarding solids, but just understand this. I cannot change the concentration of a solid by adding more solute to the pile. By adding more solid, the concentration won't change. If I were to remove any of the solid, I would change the volume at the same time changing the number of moles. So you cannot change the concentration of a solid, so they will not be included in equilibrium expressions. The same can be true for a pure liquid. Not something aqueous, but something that is a liquid. So when I take liquids, we could take water as our primary example to make sure we understand what's going on. We know from the periodic table that the molar mass is 18.02 grams per mole. This 18.02 grams per mole is always the truth for water. That's how many grams it has per mole. If we were to look at its density, it's 1 gram per milliliter. So what I wanted to try to figure out is what would the mass of 1 liter of water be? And then from there, what would the molarity of water be? So if I know the mass of 1 liter, I would then be able to plug that in to figure out molarity as well, because molarity is just moles per liter. So if I figured out the mass of 1 liter using the density, hopefully you understand that if this is 1 gram per milliliter, the mass of 1 liter is going to be 1,000 grams. If you don't understand that that's 1,000 grams, you need to come see me about what a milliliter means and how many milliliters there are in a liter, because there are 1,000 milliliters in a liter. So there are 1,000 grams in a liter. If we were to then convert that into moles, we would divide by 18.02, and we would get 55.5555, so we'll call it 55.56 moles of water. 55.56 moles of water is an important number, because if I were to take that many moles and put it into 1 liter of water, my molarity would be 55.56 moles for every 1 liter, which is a 55.56 molar solution. So what would happen if I wanted to add more moles to my solution? By adding more moles, not only will the value of the moles increase, but the number of the volume will increase. And it will increase at the same rate because the density doesn't change and the molarity doesn't change. So even if I add another 1,000 milliliters, another 1,000 grams, that's going to be another 55.56 moles, and it's going to be another liter. So I will have still a molarity of 55.56 molar. Water's concentration cannot change. So what we're going to end up seeing with equilibrium is that when we're writing K expressions, you may only use gases and aqueous, because those are the things that I can control the molarity by changing the volume or changing the number of moles inside the system. Remember, you can dilute an aqueous solution. By adding more water, we can change the molarity. So what ends up happening in these equilibrium expressions is we can only use gases and aqueous solutions.